Okay, well, let's look at another image charge problem, namely a point charge which is near a grounded sphere. So here's our sphere. Capital R is the radius. It's grounded, so the potential on the surface of the sphere and inside is equal to 0. We have a charge out here plus q at a distance a, and the origin is of course right at the center of the sphere, so a is that distance that we show here. We choose this first along the y-axis. We're going to change that, but right now that's how we'll represent it. Q prime is the image charge, and so we want to know where it would be best to locate it. And the first thing is it should be inside, because if we have this turning out to be a negative charge, then we want the surface to be at 0 potential, and so it makes sense to put that on the other side of this boundary in order to get 0 on the surface. Secondly, the symmetry of the problem is that we could spin the whole problem about this axis and it would not change. It certainly makes sense to put q prime on the axis that we show here in order to get that kind of symmetry. So we're going to place this q prime on the axis a distance b away from the origin. And so that'll be our initial guesses as to where those should be. And the first thing, of course, is to determine b and q prime. To find b and q prime, we need to find the potential at 2 points on the surface of the sphere in order to get 2 equations. So we're going to pick p1 and p2, and it's much easier if we pick those points on the y-axis. Don't forget this is grounded, so therefore the potential on the sphere is equal to 0. So what do we need? Well, we just need the distances, and so q prime is a distance b plus r, capital R, to p1, plus q is a distance of a plus r, and so we've pretty well set up to get the potentials. So we'll start by looking at p1 in terms of the potential due to q prime, and then we'll do the same thing for q and add the two together. So here's the v due to q prime at p1. It's just kq prime over the distance between the charge and p1. Putting that in, the distance is r plus b. Here's the potential due to q prime at the point p1. The potential due to q at p1 is the same thing, except now we have this distance, q to p1, and that is going to be a plus r. And so putting that in, then we have the potential due to q at p1, kq over r plus a. Add the two together, so we do that right here, and then we say p has to be at 0, so that potential is 0. So we set this equal to 0. Putting this in a different form, we can say that we have a equation number 1, which we will need to get the b and the q prime. So now let's look at p2, and for that we'll look at those distances. So here's our equation 1, and we can get that pretty easily. We require this potential to be 0. If we do, we have 2 equations. This one here, this is the equation for p1, this is the equation for p2. So that's the equation 2 right here. So all we've done is followed our recipe for the point p2. Mathematica has an operator called solve, and you put in one equation and a second equation and solve for the unknowns, and I've taken qq to be our q prime. So the answer is right here. Q prime is equal to minus q over r over a, and the distance b is r squared over a. And so I've repeated those right here. So here's our b and here's our q prime. These are the desired parameters. If a indeed give v at any point equal to 0 on the spherical surface, we're almost done. So we want to test this relation, find out if the boundary condition v equals 0 holds for any point on the sphere. We'll pick a point p3, and I've shown that up here. If you pick it off the original plane, you can always rotate the sphere to get the p3 in the plane of this drawing. We're also going to switch y to z because we're going to introduce angles, and this would be the polar angle, which is defined in terms of the z-axis. So here's our p, And if we go back to our notation for funny r, the vectors, these are the funny r vectors from the point charges to the field point. If we look at this point P3, we're at a distance r equal to capital R, and so our funny r magnitude is equal to a squared plus r squared minus 2ar cosine theta. So this is the law of cosines in order to get this relationship. And so what we're talking about is this distance right here. And that first depends on theta. R2 has a similar relationship, and so here's R2, and again this should be the magnitude of R2, and it's b squared plus r squared minus 2br cosine theta. So our total potential for the point P3 will be k, which is 1 over 4 pi epsilon naught, times q over r1 minus q prime over r2. The minus sign here is because q prime is negative, and here's our value here. So using trig on this figure and eliminating q prime, we can solve for the v total in terms of r equal r. So this would be for the point P3, any P3, and that gives us q over 4 pi epsilon naught, or k times q. And then here we have the first term, 1 over r1, and then minus r over a, which is this factor right here. And the minus sign takes into account this minus q, and we then have the other denominator to give us the total potential on the sphere at a point P3. Just to remember, this is any point on the surface of the sphere. Here it is again. If you look at these two equations and now put in b and do a little bit more algebra, what you can find is this term here and this term here. They're equal to each other. You end up with 0 for all theta and phi, which means for any point on the surface of this sphere where r equals capital R, we satisfy the boundary condition that v equals 0 on the surface of the sphere. Our values of a and b in fact give us the boundary condition that v equals 0 all over the surface. Let's find the field at the point P outside of the sphere. So this is really what we're after. The equation that I gave you before for the point P3 is right here. So this is given by this expression here, and we know what b and q prime are. If you just replace capital R with the distance r, you will then have the equation for the potential at P, because exactly the same notation and algebra was done to get the point P3. It just happened that this was at a distance capital R. If we do that, if we just put in r's wherever there are capital R's, we have the expression for the potential at the distance r. We go back to sticking in the b values right here, then find the v total for any arbitrary point, and here it is right here. In fact, all I've done to go from here to here is to put in the right value for b, which is right here, and then put little r where there's a capital R, and so we now have the general equation for any point P, and if we let little r be capital R, it'll give us 0. What about the other boundary condition, which is when we go to a distant point, so we'll let little r go to infinity? Then if you take a look at the equation here, you have r's in the denominator, you have little r's in the denominator here, little r here, little r here. If you let r go to infinity, those will take v to 0, and so we have all the boundary conditions satisfied. If we just take a look at our equations, I'm just going to run through these just to remember them. This is one of the boundary conditions for the vacuum metal interface. So you have the potential just above the surface of the conductor, and so solving for sigma, you then have an equation for finding the surface charge density in terms of this potential that we just derived. If we want the E field, we take the gradient, but the potential only depends on the distance r. If you put that in, then you're only going to have one term for the gradient, and that will be equal to this quantity here. And in this case here, this is the rth component of the vector, so this is the magnitude of the e vector in the rth direction. Now we can find the sigma free, and so that's going to be equal to this equation evaluated at little r equal capital R. And so that'll be this quantity right here, just putting in the correct derivative. And so it's minus epsilon 0, that's this part right here. Then here's our gradient or potential derivative in the nth direction, which is little r, evaluated at r equal capital R. And just repeating then, replacing little n with r, we have this equation here. So minus epsilon 0 times this derivative evaluated at little r equal capital R. So that'll give us the free charge density on the surface. If we want the total charge, we simply integrate that over the surface of the sphere. So now what I'd like to do is go to mathematics. So we'll take a look at some of these things like the potential and the E fields. Here's our problem again. Here's the potential in spherical coordinates. The first thing we're going to do is define that potential, so it's exactly what we have up here, using k for 1 over 4 pi epsilon naught. In order to do some plotting, we have to convert this to Cartesian coordinates. And there's a useful function we call transform field, and allows us to go between different coordinate systems. We also want the two-dimensional version of this, because in order to plot it, we can't plot something that has 4 quantities. So in that case, we're going to just take y equals 0, and so we'll get a projection on that axis. So I can show you more about the program, but actually what I want to do is run this. We get the Cartesian coordinate potential, so this is 3D, and so we have it in x, y, and z. This is what it would look like. Then we're going to set y equals 0. That's this quantity right here. We're in the plane where y equals 0. Here's the plot of the 2D potential function. So v is the axis in this direction here. This is x and this is y. So the sphere is sitting right here, and this is the position of the charge. Now what I want you to notice is that the image charge is here. So that's inside the sphere. If you go to that particular point, you get an infinity. And if you go to the point Q, you get an infinity. And so that's why we have these two structures here. Now remember, Q prime is less than Q, and so that's why this looks a little bit bigger. It goes up quicker because of the bigger charge. The image charge gives us the potential outside of the sphere, and so we have to have it. But in reality, it's imaginary. We can pretend that it's not even there to look at the potential outside. And so what I've done here is taken this slice through here, so we're in this plane right here. Here's where the sphere is, and there the potential is all 0. And so in order to display that, I eliminate the points inside the sphere, and so this is what it looks like. Here's the sphere, and the potential there is 0. Here is the point charge. The important thing is that there's potential everywhere outside of that sphere. There's potential even here. Now you can't see it. I can show you that it's infinitesimally, but it's there. And let me just take the plot range and let's take it down so that it's more sensitive. And so let's try 1. Well, you still can't see it. This got bigger, of course. Let's go to 0.1. Well, now you start to see it. So on this side of the sphere, here's 0 here. You have a non-zero potential, which is what it should be. The potential here, having a dependence on the position, will give us an E field over here. And the same goes, obviously, for all the way around here, we're going to have E field. The slope is related to the E field. So that's what it looked like before. Now let's look at the E field. We start with the potential again, do all the transformations, and to find the E field, we take the gradient. So right here is the gradient. That'll give us the E field in Cartesian coordinates as a function of x, y, z. I two-dimensionalize that by setting y, see here's y, I set that equal to 0. I could do the E field plot, it's right here, but the vector plot is here. but it takes so long to get it to look right by adjusting parameters that I'm not going to show it. I am going to show the stream plot. That's this function right here, stream plot of the E field. And so we'll see what that looks like. There's the Cartesian version of the E field. Remember, it has three components. Here's X, here's Y, here's Z, and it's a mess, and you could probably simplify it if you wish. But here's the stream plot. So here's the point charge right here, the source of the field. It's the source of all the field in this problem. Here's the sphere right here. And so when I showed you that there was in fact potential out here that had slope, it explains why there are streamlines over here. Now it's deceiving in the fact that it looks like the E field might be as intense here as it is over here. It is not. These streamlines are just equally spaced, and so they don't really indicate intensity of the E field. But to repeat, the E field here between the charge and the sphere is very intense. Over here it's very weak. Let's look at the surface charge density. So we start all over again. We take our gradient. In this case I've just taken the derivative with respect to V total. Here's our sigma. This is the charge density as a function of theta. Because of the symmetry of the problem, it only depends on the angle theta. It does not depend on r because we're at r equal capital R. It does not depend on phi because of the symmetry. To plot this, we have to assume values, of course, and we'll show you what that looks like right here. So remember, what we're doing now is finding sigma as a function of theta. And if you wanted it to cover the sphere, you'd have to rotate that function around the z-axis. But for now, we'll just look at it in a plane. This is, by the way, the equation for sigma right here. That can be simplified also, but I'll leave it in this form. So now we go down to the plot for sigma. I've plotted it from minus pi to pi. Realize theta only goes from 0 to pi. But to go around the whole sphere, I wanted to show you what that looked like. Here we have the plot of sigma of theta as a function of theta. This direction here, this theta here, would be pointing towards the point charge. And so you have lots of charge on the surface here, and then it decays away. Now notice that it's negative. This has to do with the fact that the induced charge on the sphere is, of course, negative in response to the positive charge. Now I've got another way of plotting this, and this is to do a polar representation of the charge density. Here's the sphere right here. This would be with the location of the sphere. And the distance between here and here is the surface charge. And so this is how it would distribute on the surface of the sphere. So if you're out here, there's lots of negative charge. This is the amount of negative charge right at this point. And then as you go to larger or smaller theta, this gets smaller, like this. If you linearize theta, this is what it looks like. So right here, this point right here corresponds to this point. Over here, this point here corresponds to over here. And notice, of course, this point and this point coincide. So here's what it looks like then. Even though this looks the same, there actually is some charge sitting on this surface. You can see up here it's not zero. It's not zero. And so that's the slight difference that you can see here. And of course, you go where the charge is, you have lots of negative charge. So I think this is a good way to look at how the charge distributes itself on the sphere if you put a positive charge out here. Okay, so again, I just want to repeat. You take this charge density and you rotate it about this axis, and that'll give you a three-dimensional plot of the charge density. This plot here is in the plane of the x and z axis. So finally, let's find the total charge on the sphere. For that, we need to do an integral over the charge density. The element of area in spherical coordinates is equal to r squared sine of theta d theta d phi. We're going to set little r equal to capital R. The integral over d phi, because there's no phi dependence, that's the 2 pi right here. So doing the integral, see what we get. The q on the sphere is equal to minus qr over a. So notice that it depends on r and a, so it's not independent of those parameters. But we notice that that quantity is our q prime. So in other words, the total charge is equal to q prime. It's negative, and it's equal to the image charge. So the total charge on the outside of the sphere, which is real, is equal to the image charge inside. This is fake. So working backwards, after squeezing out what we want in terms of calculating the fields and the potentials and so on, we basically use q prime to find all of that. We replace q prime with the derived sigma of theta. This is real. This is really what happens when we ground that sphere and bring in the charge q. This is its response to the presence of q. When integrated over the whole surface of the sphere, we get the total charge on the sphere, and that's equal to q prime. And just notice that those are not equal, which is different than the case where we had the infinite plane. We got equality between those in terms of the magnitudes, but here they're different.